Alright, let's take a look at today's lesson. This is day 2 of applications. On day 1 we looked at basically two types, exponential growth and decay. Those you've seen for a few years now. Those should have been kind of familiar to you. Today we're going to look at some that aren't quite as familiar. We're going to look at Newton's law of cooling, which we actually use in calculus. Not this exact formula, but we do use the law. And a couple of other formulas that use logarithms. So let's take a look. So for Newton's law of cooling, the big T is actually the temperature. It's the temperature. So that's the temperature. Little t is time. Okay, so there's big T and little t. So T sub S, this one, is the temperature of the surroundings. So, if you're taking something out of the oven, what is the temperature of the room that you're taking the object into? The surrounding temperature. D sub, or D naught, is the initial temperature difference between the object and its surroundings. Okay, so that's the initial temperature difference between the object and its surroundings. And little t, like I said, is time. Okay, so the E and the K is a number, a constant that we typically have to find. It'll be different for each scenario. Alright, that is the Newton's law of cooling formula. Let's take a look at the next one. We have a formula for magnitude of an earthquake, basically the Richter scale. M stands for magnitude of the earthquake, so that's in our formula. Then S is the intensity of some standard earthquake, which is kind of weird. They just say a standard earthquake. What we're going to do is we're going to let S equal 1. And that's just convenient for us. We're just going to let S equal 1 on every single problem. And then I is the intensity of the earthquake. The last formula we're going to be looking at is the decibel scale. Okay, so here's our formula, where B is the decibel level of the sound, which is measured in d, little dB, that's the notation. And I is intensity, and this I naught actually has, there's a number, it's got a reference intensity. It's 10 to the negative 12 watts per meter squared. So this number, actually, if you have good hearing, this is the lowest audible sound that a human can hear. So that's why it's a specific number. It's our reference intensity. And so these are the three different formulas that we're going to be exploring. I have an example of each one. So let's go to our examples. All right. Here's our examples. Let's take a look at the first one. We're going to look at Newton's law of cooling first. So we have a cup of coffee that has a temperature of 200 degrees Fahrenheit and is placed in a room that has a temperature of 70 degrees Fahrenheit. After 10 minutes, the temperature of the coffee is 150 degrees Fahrenheit. Find the function that models the temperature of the coffee at time t. All right, let's look at our formula for Newton's law of cooling. Let's go ahead and write that down so we can reference it. So we had big T, so temperature, big T is temperature, little t is time, equals T sub S, which is the temperature of the surroundings, plus D naught, which is our difference of the object and surroundings, e to the negative kt. Well, let's keep in mind that K is a positive constant. That was specifically positive. It's a positive constant. So this negative right here is part of the formula. K is positive and the negative is part of the formula. We have to have a negative exponent. Let's think about that for a second. If we think about our work from day 1, you remember the difference between the formula for exponential growth and decay? Remember how the growth formula had a positive exponent? It was e to a positive number, and the decay was, to a negative number. Well, this is cooling. This is temperature decreasing, so we would expect the exponent to be negative because we're decreasing. All right, so that's just something we need to keep in mind as we go through this problem. All right, so let's find a function that models the temperature of the coffee at time t. So we know the surrounding temperature. Okay, so our surrounding temperature is 70 degrees. So right in place of this Ts, we're going to put a 70. 70 plus. D naught is the difference. So it starts out at 200, and then the difference between the original temperature and the surrounding temperature. So 200 minus 70. Then we have E to the, well, we don't know the K. We don't know what K is yet. So let's go ahead and kind of fill that in. Let's use this next piece of information. After 10 minutes, the temperature of the coffee is 150 degrees. So let's set our temperature to 150 and our time to 10. What we're going to do is we're going to use that information to solve for K. We need to know what K is. All right, so let's do that. So we would subtract the 70 over, and that would give us 80. So we'd have 80 equals, and then we have 200 minus 70 is 130, e to the negative 10k. All right, so then we would divide by 130, so we'd get 80 over 130, or we'll just keep writing over here. So we'd get 8 over 13, so just reducing, equals e to the negative 10k. So now we're going to natural log both sides. So we would natural log of 8/13 equals negative 10k. So we solve for k and we get negative 1/10 ln of 8/13 equals k. Now let's think about this for just a minute. We were told that k has to be a positive number. All right, so let's think about what does the natural log graph look like. So let's just remind ourselves. We did a great job graphing the other day. If you recall, the natural log comes up here at 1, an x of 1. So natural log of 1 is 0. This number is less than 1. So this number gives us a y value that's down here. So even though we don't really know, I mean, if we had a calculator we could figure it out. We don't really know what natural log of 8/13 is. We know that that's going to be a negative number because it occurs underneath the x-axis. So I have a negative number times a negative number, which gives me a k that's positive. That's what they said, k is positive, and it turned out that way. Now, when we go back to put this in the formula, so let's go ahead and put this in the formula. Let's go ahead. So we have T of T. Okay. So our formula is the surrounding temperature, which is 70. Then we have plus the difference in temperature, which is 130. Then this is our K value. Okay, this value is positive. If I put this value, in the exponent, it's going to be a positive number. We just figured out that it can't be positive because this is decreasing. That's where this negative sign comes in. Okay, so it is positive. It is positive. But since this negative sign makes this positive, we won't use it, if that makes sense. So when I write it up here, we know K has to be positive. If I take this negative sign off, this is going to be a negative number. This is K. This is positive. But I need this value up here to be negative. So it's going to be 1/10 times ln 8/15. And then that is times T. So let's get a little space in here so we can see what's going on. All right, so that's our formula. 70 plus 30, 130, excuse me, e to the 1/2 ln, I can't even read my own writing, to the 1/10 ln 8/15 t. All right, so now part B, let's get a little bit of room over here. Part B is telling us to find the temperature of the coffee after 15 minutes. Okay, so let's do that. Let's find the temperature of the coffee after 15 minutes. What would we do? Well, we would need to put a 15 for tea. So let's do that. So we're using our formula right here. So I'm going to make B right up here. So I have T of 15 is going to equal 70 plus 130 E to the 1/10 ln 8/13, and that is multiplied by our time, which is 15. So notice how there's no negative sign up here. Just want to make sure we're clear. This exponent right here is positive because the actual number itself, the actual, ln 8/15 is negative. We just talked about that. It's negative, and I need my exponent to be negative, so it is. If that's confusing to you, you can certainly turn that into a decimal. That is fine. You just need to hold all of the values of the decimal because we can't round yet. So if the whole positive negative thing is just like, oh my gosh, what is she talking about? Then just turn it to a decimal and make sure that this exponent is negative, because that's what the formula says. The exponent needs to be negative. All right. So we put that in our calculator and we get a value. We get 132.757 degrees Fahrenheit. So that's the temperature of the coffee after 15 minutes. All right, so now let's look at the very last one. When will the coffee have cooled to 100 degrees Fahrenheit? All right, so let's get some room over here. Okay. So what we need to do is we're going to have to actually set our equation equal to 100. That's going to be the temperature. That's what we're looking for. So 100 equals 70 plus 130 E to the negative 1/10 ln 8/13 T. So we work on that. We move the 70 over, which gives us a 30. We divide by 130, which gives us 3/13. So I have ln of 3/13 equals negative 1/10. Oops, that's not negative, that's positive. Equals 1/10. Let's fix that right up. Equals 1/10 ln 8/13 T. Okay. So we solve for that. We solve for T. Basically, we're going to divide by this mess of stuff, right? Move it over here. And so we get T equals 30.202 minutes. All right, and that's our Newton's law of cooling formula. All right, great. So let's look at our next problem. So here we're going to look at an earthquake. So we have the 1906 earthquake in San Francisco, had an estimated magnitude of 8.3 on the Richter scale. In the same year, a powerful earthquake occurred on the border of Colombia and Ecuador that was 4 times as intense. What was the magnitude of the Colombia-Ecuador earthquake? Okay, so first of all, let's start by writing down the formula. So our formula for the earthquake, the magnitude, was M equals, we had log of intensity over standard, and we are saying we're going to let S equals 1. For all of our problems, we're going to let S equal 1. Okay, so what I like to do is, usually you're comparing 2 earthquakes, so I like to work on each earthquake separately. I like to do a separate, line for each earthquake. So let's work on the San Francisco earthquake first. So San Francisco, it had a 8.3 on the Richter scale, equals log, and we just said the S is going to be 1. But let's do intensity of San Francisco. I'm just going to put a little S down there so we know which intensity we're doing. Now, could we solve for the intensity of the San Francisco one? Sure, we've been working with log rules for a while. You know, we'd convert it. So this would be 10 to the 8.3 equals I sub s. Our intensity of the San Francisco one is 10 to the 8.3. All right, now let's look at the Colombia one. So the Colombia one, we don't know the magnitude. That's what we're looking for. So magnitude of the Colombia one equals log of. This one says it was 4 times as intense as the San Francisco one. So 4 times the intensity of the San Francisco one. Okay, that makes sense. Well, we know what the intensity of the San Francisco one was. It was 10 to the 8.3. So why don't we just fill that in? So our magnitude is going to be log of 4 times 10 to the 8.3. Now we would just use our calculators, and we would get the magnitude of the earthquake in Colombia is 8.902 on the Richter scale. All right, great. Now for the last formula, let's look at the decibel formula. Okay, let's look at this one. All right, so our decibel formula, let's write down this formula. So it was B equals 10 log of I over I naught. And we were told that I naught is 10 to the negative 12 watts per meter squared. So that number, that I naught, though I'm going to be giving you the formulas, you know, on quizzes and tests, I'm not going to be giving you all the numbers. So you really need to know what that I naught is, 10 to the negative 12. All right, so let's see what they have. So let's see, the physical intensity is 100 times that of I naught. Okay, so the intensity is 100 times I naught. All right, so let's fill that in the formula. So B equals 10 log. So we're going to replace this intensity. Okay, we're going to replace that with this, with 100 times I naught. So 100 times I naught over I naught. That's my formula. Notice how I'm able to cancel those out. And so what I can do is, so B is going to be equal to 10 log 100. Okay, so we know that 100 is, what, 10 squared. So this is 10 log 10 squared. So we know log 10 of 10 is 2. So this is going to be 10 times 2, or 20 decibels. All right, and there we have it. That is our lesson.